In this video, I will show you how to find the resultant vector when you have two or more vectors that are acting together, even when the directions are not just north or south or east or west. The key is to organize your work, and what I recommend is making a chart like this one. Bam! You would be wise to use this chart. Now, this particular problem involves three different vectors. That's why I have so many columns. All right, watch how I lay it out. So we have three forces, and I will just call them force 1, force 2, and force 3. So I have force 1, force 2, and force 3. The last column is for the resultant. The top row is where we will record the magnitude and direction for each vector. Please keep in mind that whatever direction that we use, it has to be measured from the positive x-axis. Sometimes you have to convert. In the last row, we will record the component form for each vector, x comma y. So let's get the magnitude and direction for each vector. The chart basically leads you through the entire process. So let's just start with the magnitude and direction. We have three forces with magnitude 70, 40, and 60 pounds. So the first force, 70 pounds, 40 pounds, and 60 pounds. Okay, those are all the magnitudes. Now we have the directions. All right, the angles are negative 30 degrees, 45 degrees, and 120 degrees. All right, so this problem is a little bit extra easy because they just gave us angles that are already obviously being measured from the positive x-axis. It doesn't say bearing, it doesn't say 45 degrees west of north or anything like that. They just gave us the angle that we needed up front. Now, there's no way to directly find the resultant from this information. We can't just add these up. So first, we need to convert all three of these vectors into component form. And here's how. To get the horizontal component, you do r cosine theta. To get the vertical component, you do r sine theta. When I say r and theta, I'm talking about the magnitude and the direction. So if I want the component form for the first force, I will do 70 cosine negative 30 and 70 sine negative 30. So that gives us a horizontal component of 60.62 and a vertical component of negative 35 exactly. And we just record that information on the chart right here. Now let's do the same thing for force 2. Again, for component form, we just need to do r cosine theta and r sine theta. So that'll be 40 cosine 45, comma, 40 sine 45, and calculator. So the horizontal component is 28.28, and the vertical component is also 28.28. Again, just record that on the chart, and then move on to force number 3. You can find the horizontal component by doing 60 cosine 120, and you can find the vertical component by doing 60 sine 120. Calculator. We get a horizontal component of negative 30 and a vertical component of 51.96. And we record that on the chart right here. So now it is time to find the resultant vector. We converted these into component form so that we could add them together. In component form, all we have to do is add all of the horizontal components together, and then we will add all of the vertical components together. And we will record that here. So we get a horizontal component of 58.9 and a vertical component of 45.24. So all that's left is to find the magnitude and direction of this resultant vector. All right, the final answer will be here. So we know how to calculate the magnitude, which I will do right here. All right, because the magnitude, you just use the magnitude formula. So we will do 58.9 squared plus 45.24 squared, and take the square root of all that. Calculator. So I'm getting 74.27 for that magnitude. Okay, so that is 74.27 pounds. All right, that's the resultant force. Now we need the direction. All right, so I will do the direction right here. Now, this is a positive horizontal component and a positive vertical component. That means we are looking at a vector in the first quadrant because it's going east and north. So as we break it down into the horizontal and the vertical components, remember that the 58.9 will go here, all right, because it was the horizontal component, and the 45.24 will go here. Now we should be able to calculate the position, all right, the direction angle, theta, by doing tangent. Okay, so because we know that the tangent of theta will equal 45.24 over 58.9. So therefore, theta itself should equal the inverse tangent of 45.24 over 58.9. Calculator. Turns out theta equals 37.53 degrees. Okay, so 37.53 degrees. Sometimes we have to convert this angle into bearing or north of west or something like that. But since the directions that they gave us in the problem were all in degrees measured from the positive x-axis, then we already have the form that we need, all right, an angle measured from the positive x-axis. So this is the final answer. Kabam! Final answer. Last problem. An airplane is flying on a bearing of 170 degrees at 460 miles per hour. A wind is blowing with a bearing 200 degrees at 80 miles per hour. Find the component form of the velocity of the plane, and then find the actual ground speed of the plane. Something is missing. It should say and direction. Ground speed and direction of the plane. So let's just make sure we add that in. Let's get organized. We have two vectors that we have to deal with. We have the vector representing the plane, the velocity of the plane, And then we have the wind that's blowing on the plane, the wind velocity. And together they will form a resultant vector. Okay, in the first row we will record the magnitude and direction of each vector. And in the third column we will record the component form. So first, let's find the magnitude and direction of the two vectors. So a plane is flying at a bearing of 170 degrees at 460 miles per hour. So the 460 miles per hour, that's the magnitude. So let's write that down, 460 miles per hour. Now for the direction, I'm not going to write 170 because on this chart, we only write directions that are measured from the positive x-axis. Okay, a bearing of 170 a bearing is something that's measured clockwise from north. Okay, I'm going to go ahead and write down the other one too. So this other one is a bearing of 200. Okay, so we're going to have to convert these to figure out what the direction would be if you measured from east and went counterclockwise. But anyway, while we're at this zoom level and I can see the whole problem, let's go ahead and write down the magnitude at least for the wind. The wind is blowing at 80 miles an hour. So we have an 80 mile an hour wind. Seems pretty high, like a hurricane's coming. And that is your magnitude. So we have the magnitude of each. Now we need the direction of each. I'm going to have to zoom in for that. Okay, a bearing of 270 means that you start from north. A bearing of 170 means you start from north and you measure your angle clockwise like this. All right, so 170, a bearing of 170 would be in the fourth quadrant. And so my vector is going to be something like this. Okay, and this is my 170 right there. So it would be nice to have a reference angle. So I could get the reference angle, which is right here, by doing 170 minus 90. Can you see that this goes 90 and then it goes further? So if I subtract 90, that's going to leave this reference angle. So that's why this reference angle is 80. Okay, now for the chart, I need a direction that is measured from the positive x-axis. So this is what I actually need. I need this angle right here that I just showed in purple. And this angle is called theta. Now this angle is on its way to 360 degrees, but it had to stop short because it ran into this reference angle. So 360 minus 80, that's going to give me theta. That's why this is going to be 280. And that's the angle that goes on the chart. Okay, so we've got 280 degrees is the direction here. Okay, now let's deal with the wind. Now we're talking about the wind vector. The wind was blowing at a bearing of 200. Again, bearing is measured from the north and going clockwise. So there's 90, there's 180. A bearing of 200 is definitely going to be in the third quadrant. So I'm dealing with an angle, a vector, that's something like this. Okay, and but this blue is the 200. So it would really be nice to have this reference angle right here. Okay, I can find this reference angle by doing, what am I going to do? We were on our way to 270. So if I do 270 minus 200, that should be what's left. Okay, so obviously this is just going to be 70. All right, 200 plus 70 is 270. So I've got my reference angle. Great. Okay, now for the chart, I need an angle that is measured from the positive x-axis. I need the angle that goes like this. All right, we call that angle theta. All right, now I can see that that is 180 plus the extra reference angle distance. So 180 plus 70. So that is 250 degrees, and that is the angle that goes on the chart. All right, so 250 degrees. Now we want the resultant vector, we want the magnitude and direction of the resultant. There is no way that we can directly get the magnitude and direction of the resultant from this information. I can't just add these or anything like that. That's why we need to convert these into component form. Now, the way you convert to component form is, if you want the horizontal component, you do r cosine theta. If you want the vertical component, you do r sine theta. So for the plane, if I do r cosine theta, that means 460 cosine 280. If I do r sine theta, that's 460 sine 280. Calculator. So the horizontal component is 79.88 and the vertical component is negative 453.01. And we just record that here on the chart. Let's do the same thing for the wind. The horizontal component will be 80 cosine 250 and the vertical component will be 80 sine 250. Now, calculator. You get a horizontal component of negative 27.36 and a vertical component of negative 75.18. And you just record that on your chart. Now, we can find the resultant vector in component form by simply adding these. So we will just add the corresponding components, the horizontal plus the horizontal and the vertical plus the vertical. The resultant turns out to be 52.52 comma negative 528.19. Okay, so that's the component form. Now, we're going to need the magnitude and direction for the final answer. So the magnitude we can get by doing the magnitude formula. So we will do 52.52 squared plus negative 528.19 squared, and we'll take the square root of all that. Calculator. So I'm getting 530.79. So that is the magnitude of the resultant vector, 530.79 miles per hour. All right, remember that we're talking about the overall speed of the plane, including the effect of the wind. So that's the magnitude. Now let's go ahead and figure out the direction. All right, for the direction, pay attention to what quadrant the vector is in. The horizontal component is positive, so that's to the right. The vertical component is negative, so that's down. So we are east and south, so that puts us in the fourth quadrant. Okay, so think of this in terms of the horizontal component and the vertical component. So the horizontal component is 52.52, so that will go here. The vertical component is negative 528.19, that will go here. We can figure out the measure of this reference angle using tangent. So we know that the tangent of the reference angle will equal negative 528.19 over 52.52. However, all I care about is the positive value of the reference angle, so I'm going to erase the negative sign. We can find the measure of the reference angle by doing the inverse tangent of 528.19 over 52.52. Calculator. I got 84.32 degrees. Okay, now that's the reference angle. The actual angle, well, actually, hold on a second. I have to be careful with direction because I want to give the direction using the same format that was given to me in the original problem. So the directions were all given as bearings. So when I record my final answer, I want to record my direction as a bearing. So let's think about the fact that bearing is measured from north and it goes clockwise. So the bearing of this vector would look like this. Okay, that's the bearing. So let me write this down. Bearing. So how could I calculate this? Notice I passed by 90 degrees. Okay, a bearing of 90 degrees would have been east. And I kept going by a value of the reference angle. So I should be able to calculate the bearing by doing 90 plus the reference angle of 84.32. Okay, that's why the bearing is 174.32. So that's what I will record on my chart. I've got the magnitude, and then now I will say bearing 174.32 degrees. Go ahead and put a box around it because that is the final answer. Hey guys, that's going to do it for this video. Go ahead and click over here to watch the next video and click over here to subscribe. That way you'll get every new video delivered right to your home screen.